In this video we're going to talk about inverse functions. An inverse function is a function that turns the arrow around or reverses what the original function did. Before we dive into inverse functions, I want to review what we talked about on the first day of college algebra, and I want to look at just functions. So on the first day of college algebra we talked about introduction to functions. We talked about the idea of the domain, which is the set of all the x values. The range is the set of y values. We talked about the idea that a function is a special type of relation such that each element in the domain corresponds to exactly one element in the range. And if you remember, kind of the silly example we used was packages to houses. So every package must only be able to go to one house at a time. Now that doesn't mean that each package can't go to the same house. But the idea here is that every x can only point to one y. Every arrow that I draw, we can only have one line coming from every x and pointing to the y's. And we did several examples of this. So we talked about the domain and range, and every arrow that comes from an x, there can only be one arrow at a time coming from each x to point to only one y. Here this was not a function because we had two arrows coming from this 1. So we have an x value that points to two different y values. In other words, you have package 1 that goes to house 4 and package 1 that goes to house 5 at the same time. Now when we looked at those examples, we talked about the idea that when we look at the ordered pairs, we wanted to have no repeated x values. If we had repeated x values, then we did not have a function. So we wanted no repeated x values, and then we had a function. One of the things that we talked about also was something called the vertical line test. So this was also really important to us. We talked about the idea that if we drew a vertical line, and any vertical line that we drew only passed through the function one time, then we have found no repeated x values. So we call the vertical line test the repeated x value detector. So we wanted to use the vertical line test to determine if the graph that we saw was a function. So if every vertical line that I drew could only cross through the function one time, then we said it passes the vertical line test and therefore is a function. In example B here, we had a vertical line that actually touched the function at two places, or touched the graph, not a function, but touched the graph at two places. And at the two places that it touched, therefore that vertical line would tell us that we actually do not have a function. We have a repeated x value of 1 here, and then at the second place that the vertical line touches on the graph, we have another x value of 1. So we have two ordered pairs that have the same x value. So the vertical line itself acts as that repeated x value detector. We've detected two x values, or the same x value, repeated x value, fails the vertical line test, therefore not a function. Alright, so that's kind of a reminder. If you need to look back to your notes for introduction to functions, then you can go back and do that again. But in this section, what we want to talk about is inverse functions. So I'm going to create a function. We have this idea here that's going to represent the domain. And then on the right, this is going to represent the range. And I'm going to name this function f. And I'm going to start to draw some arrows to represent function f. So we have an x value of 3. We're going to point that to a y value of 6. We have an x value of negative 3. I'm going to point that to a y value of negative 6. 4 goes to 8. Negative 4 goes to negative 8, 5 goes to 10. So we only have one arrow coming from each x value, so f represents a function. Now I want to look at the list of ordered pairs for f. So that would be 3, 6, negative 3, negative 6, 4, 8, negative 4, negative 8, 5, 10. So when we look at this list of ordered pairs that represents the function, every first coordinate or every x value you remember, is only there one time. So that's also significant again, that we have no repeated x values, so therefore a function. Now, the idea of an inverse function is we want to turn the arrows around, so I want to reverse the arrows. So we're going to have a function, we're going to call it f inverse or f reverse. We're going to do f in reverse. Now what f does is that it switches the arrows and points in the opposite direction. So instead of going from 3 to 6, this f inverse function or f reverse function is going to start at 6 and point back to 3. So all of the arrows are going to go in the opposite direction. So we have a different starting place and a different ending place. So the inverse function, f inverse or f reverse, actually starts on the right side. So for f inverse, the right circle or oval is actually the domain, because that's where everything starts. These are the x values for the f inverse function. And on the left, that's where we end up, that's where the arrows point. That actually now for f inverse becomes the range, or these are the y values. So let's look at a list for f inverse. So my ordered pairs then would look like 6, 3, negative 6, negative 3, 8, 4, negative 8, negative 4, 10, 5, and so once again here we have the x's and the y's. So when we look at f inverse, we see that f inverse is also a function. When I look at all of the x values, there are no repeated x's. So the inverse is also a function. One of the things that we want to be able to do is to think ahead. So if we only knew about function f and the order pairs for f, is there a way that we could know that f inverse would be a function? What if I didn't want to make this list? What if I wanted to know if this list would represent a function just by looking at the original list of the order pairs for function f? So what if I just wanted to focus on the original function? Would there be any way to know if the inverse would also be a function? So that becomes one of our questions. So the answer to that question is yes. We actually don't need to make the f inverse list to decide that f inverse would also be a function. Here's what we'll be looking for. We're going to be looking for, does the original function f have any repeated y values? So when we look at the original function f, we notice that it has no repeated y's. So every y value there is only there once. So why would that be significant to the second list for f inverse? Well, if you notice, when you look at the ordered pairs, they're just reversed. So every x in the original list now becomes a y value in the f inverse list. Every y value in the original f list actually then becomes an x value for the f inverse list. So y's become x's. So if I know that I don't have any repeated y values for the original list, then when I look at the f inverse list, what I'm guaranteed is since all those y values are going to be switched, or they're going to reverse or switch places to become x values for that second list, then I'm guaranteed that no repeated y values in the original list will guarantee that I'll have no repeated x values for the second list. We call the function f, if this is true, we call it a one-to-one function. So let's say f is a one-to-one function. In other words, when you go back and you look at the original function f in red, every arrow only has one destination. So every x leads to only one y, and then every y connected back to only one x. So we call this a one-to-one function. If a function is one-to-one, then when you look at the f inverse list, you're guaranteed that f inverse then will also be a function. Okay, so the takeaway here is when you look at the original list of f, if you look at the y values, if there's no repeated y's, that actually translates to be no repeated x values for the f inverse function. And if f inverse then has no repeated x's, then f inverse is now a function. Well, is there a possibility that the inverse would not be a function? And the answer is yes, so let's look at that. Alright, so I'm going to draw some arrows. Again, here's my domain, and here's my range. So I'm going to call this function f, and I'm going to draw some arrows. So I'm going to say 3 goes to 9, negative 3 also goes to 9. Now, is that okay? And the answer is yes. Remember, if I think about the left side as being packages, and the right side as being houses, packages to houses, I'm just going to write this up here. Is it okay for two packages to go to the same house? And the answer is yes. So this is a function. So far, so good. That's okay. Let's have 4 go to 16, and we'll have negative 4 also go to 16. Still okay, still a function, and then we'll have 5 go to 25. So when I look at the ordered pairs for f, we have 3 goes to 9, negative 3 also goes to 9, 4 goes to 16, negative 4 also goes to 16, and then we have 5 going to 25. So here we have a list of all those x and y ordered pairs. When we look in the list, we notice that there are no repeated x's. So f is a function. No repeated x's. So our primary concern here is not necessarily if f has repeated x's. What we're trying to think about is the inverse, or the reverse. We want to know information about what happens when we switch the arrows around. Now when I switch the arrows around, 9 goes to 3, but then 9 also would point back to negative 3. So we're going to start to look at our list of ordered pairs for f inverse. That would be 3 goes to 9. Oops, sorry. Switch those around. We said 9 goes to 3. Remember, we're starting on the right side now. This is my domain. And now my arrows are pointing back to the left side. So this is our range. So we're starting at 9, and then we're moving in the opposite direction now to 3. So 9, 3. But then we have 9, negative 3. So we should start to see, oh, that's a problem. But let's keep going. We have 16 that's going to point back to 4, but then reversing the second arrow, 16 now points also back to negative 4. And then 25, it's going to reverse that arrow. It's going to be pointing back to 5. Now, do you see the problem here? When we look at the list for f inverse, we see that we have repeated x's. So when we look at the list of ordered pairs for the f inverse, so the reverse of the original function f, we see that we have 2 9s, 2 16s, and this is not a function. Now, could we have known that before we actually made the list? And the answer is yes. If you go back to the original list, what you're going to notice is in the original list, those ordered pairs for f, we had repeated y's. So that is a clue that the second list will not be a function. So if the original function f has repeated y values, when we go to look at the ordered pairs for f inverse, all of the y values in this list then switch or reverse to become the x values in the f inverse list. So if we have repeated y's in the first list, in this second list, that will translate to be repeated x's. And if we have repeated x's in this second list, then the inverse will not be a function. So in this case, we would say f is not a one-to-one function. So when you go back and look at the original function f, what you're going to see is you don't have one x leading to only one y, and then only one y leading back to only one x. So just looking at the arrows, you could almost say this is like a 2-to-1 function. 2 x's go to only one y. That was okay going forward, but when we reversed the arrows, that y led back to 2 x's. So f is not a one-to-one function, therefore the inverse is not a function. So here's some important facts here. If the original function has repeated y values, the inverse will have repeated x values. If the inverse has repeated x values, then the inverse will not be a function. The original function, if it's not one-to-one, then the inverse will not be a function. A one-to-one function is a function in which no two ordered pairs have the same second component. So we want no repeated y's in that original function. We want the original function to be one-to-one. If the original function has repeated y's, or if the original function is not one-to-one, then the inverse will have repeated x's and the inverse will not be a function. A one-to-one function is a function which has no two ordered pairs that have the same second component. What does that mean? That means when you look at the ordered pairs, we want to have no repeated y values. So the big takeaway actually from this page is that if we care about having a function, it is important to know that only one-to-one functions have inverses that are also functions. The key word there being function. So if you want to work with only functions, your original function must be one-to-one. Your original function cannot have any repeated y values if you want your inverse to also be a function.